Let's start this lecture 22, by overviewing what we learned on lecture 21. So in lecture 21, we learned about isentropic efficiencies. The isentropic efficiencies is basically compare actual work and isentropic work. I would say isentropic work is basically reversible work or ideal work. For a turbine, we compare actual turbine work to the isentropic turbine work. So by looking at the HS diagram, always isentropic turbine work is greater than the actual turbine work. Now, we can compare these two works in terms of enthalpy changes. So for actual turbine work, we have H1 minus H2A, where the entropy at 2A point is greater than entropy at 1. The isentropic turbine work is defined as the difference between the enthalpy at state 1 and enthalpy at state 2s, where the entropy at 2s should be the same as entropy at 1. Then how about the compressor or pump? So compressor and pump needs a work input to that device to run it. Now, if you compare the isentropic work and actual work, the isentropic compressor work is always smaller than the actual compressor work. What it means is that ideally compressor needs less work than actual case. Now, we also can define or express the compress efficiency in terms of enthalpy differences. So for the isentropic compressor work, we can express it in terms of H2S minus H1. Again, the entropy at 2S should be the same as entropy at 1. That is the condition for isentropy case. Now, the actual compressor work can be written as H2A minus H1, right? Where again, S2A is greater than S1. Now, we have the same definition of the same definition for the pump efficiency as the compressor efficiency, because again, it's essentially they are the same. Now, the pump efficiency again is defined as the isentropic pump work divided by actual pump work. For the isentropic pump work, we also can written that as H2S minus H1. Okay, so still that is the valid equation. But many times, instead we use this equation because we derived the ideal work of the incompressible fluid as this equation. Okay, so now we are going to use that expressions for the calculation of efficiencies, and that we are going to use those equations in coming along lectures. Now, let's get started to give you a lecture about lecture 21, thermodynamic cycles. Now, what I want to say is that is the start of our last part in our course. So from now on, we are going to talk a lot about thermodynamic cycles. Now, in order to discuss thermodynamic cycles, basically we have to understand how we define the thermodynamic cycle. How do we understand the thermodynamic cycle? So today we are going to, I'm going to introduce the basics of thermodynamic cycles to you. So please read chapter 6.2 to 6.4 to understand better, right? And today, specifically, I'm going to discuss the net work output and thermal efficiency, then how we understand the net work output and thermal efficiency here. Okay. What I want to emphasize is these two are two very important critical quantities that you have to calculate all the time when you discuss the thermodynamic cycles, particularly when you have to understand performance of thermodynamic cycles we always have to calculate the net work output and the thermal efficiency. And based on that, we also will discuss the cooling rate and coefficient of performance for refrigerator later. Now, before we discuss thermodynamic cycles, we have to understand reservoir or heat reservoir. So this reservoir is a very special term in thermodynamics to describe a very ideal thermodynamic space, right? Which is very ideal. That has a very large thermal energy capacity. What it means is that, even though there is a certain heat input or heat loss from this reservoir doesn't change its temperature. So that is very important. So no matter what happens, even though there might be certain heat loss from the heat reservoir, this reservoir doesn't have any temperature difference. Same way, even if the reservoir gets certain heat out of from some air, this reservoir doesn't change its temperature. Then, how can you apply this very ideal thermodynamic kind of conceptual space to reality? Now, if you really think about like a big big kind of the spaces like ocean, river, lake, or even atmosphere. If you really think about them, okay, let me just show you this. So like atmosphere, river, lake, and ocean, so they are so gigantic and huge such that even though you just give certain heat to those kind of big spaces, they wouldn't change their temperatures. Like even though, or if you just want to take out certain heat out of those ocean, lake, atmosphere, or river, you can easily imagine that, their temperatures wouldn't change that much. Okay. Then, can you really then, always should you really think about the reservoir to be really huge and gigantic? Not really. You can model a system as a reservoir as far as its thermal energy capacity is large compared to the amount of energy it supplies or absorbs. Now, for example, again, let's assume that you have a very big room where we have one TV. And obviously TV emits certain heat, transfers certain heat out to the room, right? Because there is certain kind of components inside the TV that generates heat. But if this room size is bigger than TV, the temperature of the room wouldn't change. Because of TV. So in that case, even though the room itself is not that big, compared to the size of river, lake, or ocean, still we can assume this room to be a reservoir. Okay. Now, there's one example, and there are many other examples, like such as a two-phase system. Let's say that you have water and ice mixture. and they are in phase kind of change processes. So now you can easily think that this mixture of water and ice should maintain the temperature at 0 degrees Celsius. So even though there might be certain slight heat input or out, still you can easily assume that your mixture still can remain its temperature at 0 degrees Celsius as far as you have ice and water there. So that can be also considered to be a reservoir. Industrial furnace is so huge, compared to like other components. So that can be also, considered to be a reservoir. And as I already said, like air in a room, like inside inside a room, which is much bigger than the TV that is installed inside the room. So in that case, actually, room or air in that room can be considered to be a reservoir. So now we can like consider a lot of kind of different examples for reservoir. If we really classify those reservoirs into two cases, then we can classify one type of reservoir as heat source or energy source. And another type of reservoir is thermal energy sink or heat sink. So the heat source always gives certain heat to the system or to somewhere else. Now, still, this reservoir or heat source shouldn't change its temperature. Right? So that satisfies the condition of a reservoir. Or heat sink does have certain heat, absorbs heat from some air, but even with that heat absorption, this heat sink temperature, at low temperature basically, does not change either. Let's assume that we have one heat source and one heat sink, and they are together. Then what you can imagine would happen is there should be direct heat transfer from heat source to heat sink. Now, is that really beneficial to us? Not really, because that is a spontaneous process. So as far as we have heat source and heat sink, and it's very natural that there is a heat transfer from heat source and heat sink, and there's nothing that we can benefit out of this process. Now, our motivation and question is, can we make use of this heat transfer by using a cycle, thermodynamic cycle? So that is our main question.